introduction. I'd like to thank the organizers for inviting me to this wonderful conference. I'm learning a lot about statistics because it's not my field of expertise. So the reason why this whole work was possible is thanks to this collaborator, Davide Fabbrico, former PhD student at the University of Firenze in statistics. He defended his dissertation last year in Bayesian inference. And we're friends. I've known him for a long time, so sometimes we try to find common ground, and that's how this research was born. And the topic is the use of statistical tools to rigorously analyze data produced by numerical algorithms. I'm more of a spline guy, actually. Typically, when I run simulations to solve PDEs, there's some discretization parameter. It might be the step size of a grid, or the mesh size, or the spacing of nodes if we work with point clouds and so on. This is denoted by h, and then we expect the error to decay as a power of h, usually as we refine the spatial discretization. And we're interested in showing that the method converges with some power k, not only from a theoretical point of view, but also with numerical experiments. And we propose a statistical tool to better analyze the convergence data that we get from experiments. And I'll motivate the reason later in the talk. So the advantages are that in this way we can estimate the convergence rate in presence of noise, which otherwise would be hard to do. We can get an estimate of the uncertainty in the estimation. So we can say convergence rate of 2 plus or minus 0.1. We know how confident we can be in the convergence rate that we observe. And we can maybe optimize the number of numerical experiments we need to perform. Otherwise, it's always a wild guess, maybe 5, 7, 10, who knows, right? How many to perform. So this is what a typical error plot looks like. It's a sample from papers published recently on the archive in the numerical analysis section. And basically more than 30% contain at least one of these plots. They come in all sizes, shapes, and colors because everyone has their own plotting routines. But they have some elements in common, right? So we're trying to deduce k. It's like a power law. So we plot things in log-log scale so that h to the k behavior becomes a line with slope k. And we have reference lines dotted or highlighted in some other way. We can compare the decay of the errors to these reference lines. This is really typical. Okay. And in numerical analysis, there are two ways to get clarity and to understand the methods we use. We can analyze these methods from a theoretical point of view, and this culminates in proofs. Or we can gather experimental data. And as mathematicians, we have very high standards of rigor when it comes to proofs. We cannot publish a leaky or messy proof. We often don't have as high standards when it comes to the data we gather and how we elaborate the data, unlike experimental sciences like physics, chemistry, and so on. They always do statistical analysis. But it's extremely rare to see anything more than a simple reference slope. So I asked myself why, and there are a few reasons. Some of these are philosophical. So, okay, we can maybe discuss over coffee or beer. For example, from an epistemological point of view, I think many of you would say that numerical experiments are inferior in some sense to proofs. At least this is the default mathematician's point of view, I believe. I don't fully believe it myself. I don't really buy into this all the way, but maybe 90, I only disagree 90%, okay. It's always been done this way, undeniably. So we keep doing it this way because nobody would ever complain and we can get the papers published. Often we don't know enough statistics to do better. I managed to get a master's degree in mathematics without taking a single statistics course. Then I studied more later, but just to say it's not mandatory in many cases. And perhaps we don't need more than a reference slope to check convergence anyway. And the first three objections are, as I said, philosophical or personal or subjective. But at the last one, I would like to debunk in this talk. So, okay, the simplest approach is to do linear regression. And it just takes one line of code in MATLAB if we want to do that. There's a fit command. We fit the log10 values. So we have an array of h values, an array of errors. And this way we estimate the slope k and the intercept. So basically the height of the line gives us also an estimate for the constant in front of the h to the k term, which is nice when we want to compare different methods for the same problem, of course. When we change the problem, c also changes. So if we do automatic software testing, maybe we have a large library, we do a lot of changes, then we want to see if we broke anything, we introduced any bugs. We can do automatic estimation of convergence rate to be sure that our finite element code still works after the change, for example. Or we can tune parameters of the algorithm when we do some grid search to optimize C, maybe, instead of K. Or maybe there are too many numerical experiments to put in a paper, so we do it automatically instead of visually. And lastly, we can try to optimize the number of experiments required to achieve some uncertainty threshold in the estimation of the convergence order. So where does the noise come from? Because okay, convergence plots can be very smooth sometimes, but in general, we cannot expect them to be perfectly straight. So the noise comes from the use of stochastic sub algorithms. If we do Monte Carlo integration, clearly we will have noise in the convergence plots. But it could also be that H is in the pre-asymptotic regime, or maybe there are round-off errors that are then amplified by poor conditioning, or simply the arbitrary choice of a mesh or a point cloud to work with, or the initialization of an optimization algorithm, the initialization of an iterative algorithms. Sometimes it's random, sometimes it's arbitrary in the sense that we set it to 0, but we could have set it to any other point. So effectively, this introduces noise. This is an example of a noisy error plot. We do a linear fit. The slope is 2.13. MATLAB gives us also a confidence interval that's 0.99 to 3.27. Okay. Can we claim h squared convergence given this confidence interval? I wouldn't say so, right? At least I would object as a reviewer of a paper if someone claimed that it's clear from this picture that this is h squared convergence, if this is the confidence interval we get, right? So, okay, let's enlarge the data set then. Let's add more points. The right one is a superset of the left one. From 7 points, we go to 13 points. We do the linear fit again. Well, the confidence interval is now 1.27 to 3.44. We haven't really improved much. So, okay. How can we better understand what's going on? And the idea was to model the errors as random variables. So the fundamental intuition here is that for a fixed value of h, we can model the error at that discretization step as a random variable xh. Not only in the case of stochastic algorithms, I made this example of Monte Carlo integration earlier, but also when we have deterministic methods subject to arbitrary choices, like the construction of a mesh. Many people presented work on with splines on triangulations. Okay, but how do we find a triangulation? There are infinitely many high-quality triangulations we could choose from on, let's say, a potato-shaped domain. And it's just arbitrary. And when a software computes one for us, it's effectively sampling a random mesh among the space of all possible meshes for some quality parameter. So in principle, these errors can have two distinct rates of convergence. One is the decay rate of the mean errors, and one is the decay rate of the standard deviations of the errors. So imagine these Gaussians getting smaller and smaller and getting closer and closer to zero. But in principle, this could happen at two different rates, K1, K2. Okay, but then we would get a very complicated model. And this is not, in practice, we observe K1 equal to K2. So we decided to adopt this simplified model with a normal distribution with mean C mu, H to the K, and the variance is C sigma HK squared. So the standard deviation is C sigma HK. And what are the assumptions? Well, the normal distribution, which has to be checked for some algorithms before we apply the model, of course. The independence of the errors. And well, this won't apply if we refine the same grid, right? Because for smaller h, we don't have independence of the errors anymore. So for example, if you do mesh refinement, then maybe this has to be checked again. It's not obvious that this might apply, but let's assume independent grids. So we remesh every time as we refine h. And as I said, the same rate. Note that the h-indexed family of random variables is heteroscedastic. So basically the variance is changes, right? So it's already the linear regression I did earlier is not really the right thing to do in this context. So for unsigned errors, we use the same or with a folded normal distribution. It's like the absolute value for normally distributed. And well, when we approximate the value of an integral, for example, we can overshoot or undershoot the value. So the error has a sign. But if we have a solution of a differential equation, we typically look at the norm or the distance between that solution and the reference solution. So it's a norm, it has no sign. So we also have a model for unsigned errors. And the model reproduces the smooth and noisy convergence behavior depending on the ratio of C mu and C sigma, those two constants. So in the left case, we have the smooth regime, and I chose, basically I sampled the random variables, okay, with C mu equal 8 and C sigma equal 1. So the C mu is larger than C sigma, and we get this smooth convergence behavior. But with C mu equal to C sigma, we get this erratic convergence behavior, but it's still H to the K convergent. Clearly, this is converging with rate K, right? So it's not that the method has lower order or there's anything wrong with the method. It's just a different value of the ratio C mu over C sigma. Okay, so, and the ratio depends on the numerical method, the choice of discretization, also input data. So it depends on the equation you're solving or the function you're, but I won't elaborate on this. I just want to show you that the normality is sensible, is a sensible assumption. So here we have an example of trapezoidal quadrature for a Poisson point process. So basically some random points in a unit interval. We approximate the integral, should be -3. No, sorry, should be 0. This is -3 times 10 to the -8. Okay, and it's like this Gaussian looking thing. Centered at -3. And this is a cumulative distribution function for a finite element method with linear elements on a torus with several different meshes. So we have lots of different meshes and look at the errors, and we basically don't see a difference between the normal distribution CDF and relative errors in the L2 norm, H1 norm, L infinity norm. So seems like the normality assumption makes sense, and that's probably because the global error is the sum of local weakly dependent contributions. So by some central limit theorem argument, we probably get this normality. Okay, so I'm glad that the previous speaker already introduced Bayesian methods. It's not that this is the only way, of course. There could be also a frequentist approach to the estimation of K and the other parameters. But as I said, Davide is an expert on Bayesian methods, so that's why we went that way. For those who don't know, frequentist and Bayesian is like saying splines versus wavelets or kernels. So, okay, but we denote by theta the vector of parameters in our model. So C mu, C sigma, K, those would be the parameters we want to find from data. And by Bayes' formula, the posterior distribution is something we can get from a prior distribution on the parameters and the data. So we have some prior beliefs on, or let's say we expect the parameters to have some values before looking at the data. Then we look at the data, we update our belief. And the probability distribution on the parameters will shrink around the values which will correspond to the convergence order and so on. So these are the densities, probability densities of the distributions. So once we have the posterior distribution, we can compute the mean, standard deviation, and so on to get K plus or minus some value. And we reformulate the model like so, at least in the signed case, with this 10 to the beta mu instead of C mu. So what is going on here? Basically, we need to, in the Bayesian framework, we need to choose a prior. So a probability distribution before looking at the data. And we have no idea what the convergence order might be. We have no idea what the constant in front of h to the k might be. So we just say, oh, well, it could be uniform. It could be anything. Everything is equally probable. K could be -8, -7, -6, and so on, all the way to 8. But this is an arbitrary cutoff. Okay, it could be 12 or 16. And the betas as exponents mean that we have a uniform distribution in logarithmic scale, which is kind of what we usually assume. So we don't know the order of magnitude. It doesn't matter if, otherwise, we cannot take the uniform distribution on 10 to the -8 to 10 to the 8. You get why. Having fixed the prior distribution, which gives us P of theta, so the probability of having some parameters theta, and the model, which is the normal model of the errors I presented earlier, we can compute the probability of observing some data set given a fixed set of parameters. And we now know the posterior distribution, P of theta given data, up to a normalization factor, P data, which was here, the normalization factor. How do we sample from the posterior distribution if we don't even know P data? Well, that's where the Metropolis Hastings algorithms comes to help us. So we initialize theta 0 by sampling the prior distribution randomly, and then we define a sequence of theta i's, which will be samples from the posterior distribution by defining at each iteration a theta prime. That's like a random perturbation of the previous vector of parameters theta. We calculate the acceptance ratio with this formula using the probabilities I mentioned earlier. This is alpha. We generate a uniform random number u in 0, 1. And then if u is less than or equal to alpha, we accept theta prime as the next element in this Markov chain. So it's like, imagine doing some kind of random walk in this space. I'm saying this for the benefit of the Spline community, of course. The statisticians know this very well. And otherwise, we reject the step and keep theta I equal to theta I minus 1. And we try again until we reach the end. This M, it is a very large value. So for example, in my experiments is 300,000. But it's a very cheap algorithm, right? It takes very little to run one loop. And the variance of this random perturbation is tuned so that new steps are accepted around 23% of the time. This is in some sense optimal, or at least close to optimal. This is something we want. So this is what the posterior samples look like for K. So we have 10 to the fifth, 2 times 10 to the fifth, because we reject the first third, which is like a warm-up time for this iterative algorithm. Then the chain mixes, and basically the values for K jump from, well, 3.3 to 3.7, but you see that they mostly concentrate around 3.5. And that's because I ran the Metropolis Hastings algorithm on data that was generated from a model with order of convergence 3.5. So we can also detect fractional orders of convergence. And this is what the posterior distribution looks like for K. And you see the peak at 3.5, and basically there's the support doesn't reach 3 or 4. So if we have something like this, I think we can be quite confident in saying that the order of convergence is 3.5, or at least we know what the uncertainty is because we've quantified it. So to validate the Bayesian approach, we do exactly this. We fix theta bar, we generate, oh, sorry, that's usually the mean. I'm sorry, this is probably not good notation for people in statistics. Generate data using the normal model, and then run the Metropolis algorithm to recover a probability distribution, which we compare to the value which we use to build the synthetic data set. So for example, here, we have 3.5 as the order of convergence. C mu is 10 and C sigma is 1. And that's because this one is the beta, so the exponent 10 to the first gives us C mu equal to 10. So the ratio is 10, is away from 1. We are in the smooth regime, and by increasing the number of data points in the convergence plot from 7 to 13, we notice significant reduction in the standard deviation of K. So from 3.46 plus or minus 0.04, we get 3.49 plus or minus 0.01. Okay, that's very good, right? We know that the convergence order is 3.5. But what about the other regime, which I called variance-dominated regime? Here, the ratio is just 1, so we can expect noisy convergence plots. And indeed, the estimation has much larger standard deviation. So you see 3.58 plus or minus 0.17. And if we bring the number of points to 13, then it's 3.56 plus or minus 0.13. We have to go to 100 to get 3.49 plus or minus 0.05. But at least we know how many we need to put to get a reliable estimate of the convergence rate. Otherwise, the plot would look something like, can you all see it? Something like this, right? So we can try to do a best fit, but how many points do we need to be sure? And I'd like to end with a case study. Time's up. So one of my research topics is the construction of quadrature formulas on scattered nodes. Any questions? No. Okay. So we want to prove that, or at least experimentally, that the errors go to 0 as the field distance, so the largest gap in the node distribution, goes to 0. Unfortunately, the convergence of these meshless moment-free quadrature formulas often falls in the variance-dominated regime. So this example you see here is for the construction of quadrature formulas in the interior of a 3D torus in 3D. So what is the source of this noise? And what is K? Because you see in red one slope, which is plausible, and in black another slope, which is also plausible in some sense. But one is h to the third, the other is h to the fifth. These are high order methods. So it's not easy to establish the right order of convergence. So the nodes are built with an advanced in front method. We start by placing some nodes, and then we place some more in the interior, trying to keep some quasi-uniformity of the nodes. So not big gaps, no big clusters, and the nodes are generated by a random process anyway. So the quadrature errors are a function of the seed of the random number generator. We can change the seed and see how the error changes. This is what the nodes look like after generation. This is a slice of the torus. We have nodes on the boundary, nodes in the interior. This is the library that I use. If you need to generate nodes on complicated 3D domains like CAD domains, yeah, let me know, because I can maybe share some code. And this is what the convergence plots look like for 8 different seeds. So seed 1, seed 2, 3, 4. This is too noisy, at least we thought, this is too noisy to publish. And cherry picking the best one is, well, scientific fraud. So what can we do? Okay, I mean, he who is without sin shall cast the first stone. So I mean, but we didn't want to do that. Okay, so standard fix is to average errors over seeds to reduce variance, and John has taught us by how much it will be reduced. Right, so I don't need to say it. And when we plot the averaged errors, we get this curve, and the linear least squares fit gives us k equal 4.4 with 95% confidence bounds, 3.4, 4.4. Okay, so order 4, maybe more. Okay, this was a simple fix, enough to publish the paper, but the runtime has grown by 8 times. The exact order is still unclear, and we don't really have an estimate on the uncertainty. So last slide. Let's now apply our Bayesian approach, because the theoretical analysis of this method predicts h to the 4th, at least. Then it could be higher. And actually, we have observed super convergent behavior. So we see in many cases that the experimental order of convergence is larger than 4, but extraordinary claims require extraordinary evidence, right? So when we use this least square fit, we don't have enough evidence to really claim superconvergence, at least in my opinion. But with the new statistical approach, you see with only one seed and 8 different values of h, we get 4.69 plus or minus 0.24. Okay, could be just a coincidence. Could it be that it's 4? But then as we add more seeds and the number of data points becomes larger, we get 4.69 plus or minus 0.15. Now the chances that it's just a coincidence are much lower. So maybe now we're confident enough to say that it's super convergent. And if we're not confident enough, we can keep adding more data points and see how the standard deviation decreases. And I'd like to end by saying that, well, there's one more convergence which we need to check, which is convergence to lunch. So, okay, thank you for your attention.